All right, class, welcome to section 4.5, last section of this chapter. Okay, Lagrange multipliers is a method invented by a French mathematician named Lagrange. And so, well, obviously, if you get to make up a new method of solving, you get to name it yourself. Euler made up his own new number. He got to name it after himself. So I'm just hinting, maybe if you want your name out there, invent something really important that people will use for generations to come. So, the Lagrange multipliers. Our task at hand is to optimize a function of several variables, which we're going to call the objective function, given a certain condition called the constraint function. So if you remember from section 2.3, we had quite a few of those annoying functions. We had to minimize or maximize, right? Again, what does it mean to optimize? Find the min or max. All right. And if you remember in chapter 2.3, as I said, there are quite a few of those problems where the function actually came up to have several variables. So one such example was a problem that we've done quite a few times that said, find the maximum possible area of a rectangle given that find the maximum possible area of a rectangle given that the perimeter is fixed. And let's say we fix it at 200 feet. Okay, so let me just remind you of what we did. We drew a picture, by the way, of a rectangle, and we said what? Well, a rectangle has a width and a length. It doesn't matter which one you label what. So let's say the y is your length and x is your width. Okay, fine. And then what did we want to do? We wanted to maximize the area. So what's the area of a rectangle? The area of a rectangle is x times y. So as you see, you are trying to maximize a function, but this function depends of several variables. This is our objective function. Right? This area is a function that depends on both x and y. Yes? All right. But we are given something. Given that what? The perimeter, what is the perimeter of a rectangle? Is 2x plus 2y, right? So add up all the sides. Now the perimeter is fixed to be 200 feet. This is your condition, right? That's what we're saying. Fine. Maximize the area, but this is what has to happen. You can only put 200 feet of fencing, let's say, around this enclosure. That's it, no more. So this is your constraint function. Okay, that's your objective function. Your objective is to maximize this area under this constraint, right? So we're constraining your rectangle, and that's what I'm doing. I'm constraining my rectangle to only 200 feet possible around it. That's your objective function, okay? That's your constraint function. Good. So, again, as you see, it depends on two variables. Now, what did we do back in chapter 2? Oh, easily. We had to solve this equation for y, or x, but we solved it for y. And then take the y value, plug it in here, and then all of a sudden you have a function of one variable only because we replaced the y with something that had an x in it. And then we went back to just maximizing functions of one variable only, okay? Now this is okay and easily done. Why? Because this equation is super easy to solve for y. plug it in here, it's not going to make it a super ugly function to take the derivative of. It's actually very nice and simple. So no problem, we can still do that. However, many times our constraint, our condition is extremely ugly. It's not an equation that's easily solved for one of the variables. This is y equals to basically what? 100 minus x? That's easy, yes? It's a linear function or linear equation. Sometimes, what if you have squares and cubes and square roots and I don't know what, logs, crazy stuff, yes? It's not going to be easily solved. If it is, and you plug it into your objective function, that could be extremely ugly, right? Remember, you have to take its derivative, its second derivative. So these could get complicated really fast. Okay, so what did Lagrange do? He came up with a new method. That's his method. Said to optimize, in other words, what? Minimize or maximize an objective function, as you see, that is made up of two variables, subject to a constraint equation. And again, I'll show you what that means, where this equal to 0 come from. But subject to a constraint, to some other condition, right? Which, by the way, is an equation. Yes. All right. What we're going to do is we're going to be, in fact, creating a new function. We call it L for Lagrange, right? And it has, as you see, it involves this same function f of x, your objective function, minus lambda times this constraint function, okay? So it looks more complicated. However, it's a function of three variables now, the x, the y that you already had, and it's introducing this new variable called lambda, which is the Greek letter lambda. I think it's lambda. I might have b in it, by the way. I'm not so sure. Okay. And then we're creating this new function, and we're going to maximize this new function. So instead of having two things to worry about, we're putting them together into one function, kind of like our d-test before. We had four second partial derivatives. We combined them into one function, which was our d-test function. Okay, so we combine these into one function, which we call L of x, y, and this new variable lambda. And then all we have to, in fact, do is find the critical points of this function, right? So again, how do we find the critical points? Find the first derivatives, yes? And set them equal to 0, yes? Now, as you see, there's no d-test involved. This is it. All you have to do is find the critical point. It turns out the min or the maximum that we're asking you for will occur at one of these points. So in other words, what I'm saying is the solution to the problem is simply the critical point of this new function. So by the critical point is the x, y, and lambda, but again, what are we just choosing? The x and the y values of them. That's what we're interested in. This lambda, as a matter of fact, we'll see has a meaning itself, yes? But the solution to the initial problem, what initial problem? Maximizing or minimizing this function f occurs at this critical point. No d-test is needed. Oops, sorry, no d-test is needed. The solution is the critical point. In other words, trust that if we ask for a max, the critical point produces the max. Now, sure enough, if we were in a calculus class, right, we wouldn't tell you if it's a minimum or a maximum. You'd have to figure that part out. And that's not so easy. You also wouldn't even use these Lagrange function. You would use gradients, and it's calculus. It's a calculus 3 problem. Let me just put it that way. Okay, so we oversimplify it. It's a great problem to be able to solve in business calculus. It's got applications. So we are oversimplifying it for you, and we're telling you, hey, this is it. Just trust us. Just find the critical points. We've practiced how to do that. The problem answer is in that critical point. That's all we're asking you to do. And just trust that we're telling you. And again, as I said, in calculus, you will say optimize. In other words, figure out, is it a min or a max? Now we're just saying maximize under this condition, right? So in other words, whatever answer you get, be sure that it leads to a maximum. So we're not making you do this d-test type of thing, which again, you wouldn't use the d-test in Calc 3. But what I'm saying is, that's it. That's all we're asking you to do. Trust us that the critical point we're asking you to find is indeed minimizing or maximizing the problem, right? Whatever we're asking you to do. Does that make sense? All right. So let's get to our problem. Okay, let's get back to, you see I got a blank page next because I'm going back to my problem here. So I keep that there. So what was my problem? To maximize this objective function, the area of a rectangle, which is x times y, yes? Subject to this condition, and this condition was that the perimeter is equal to 200, okay? So this is our objective function. So what this says is that what you're going to do is you're going to make out of this function one that equals to 0. So just to kind of make it into that notation. So just to match this a little bit, I'm not going to call it area, I'm going to call it f of x. That's your objective. And out of this condition, you're going to create yourself a new function, g of xy, which is whatever you would get if you'd set this equal to 0. So in other words, 2x plus 2y minus 200. Yes. So what we're saying is take all terms and throw them all on one side of the equation so you have everything in here. Yes. Okay. So out of these two, the objective and the constrained function, create yourself the lambda function. I'm not the lambda, it's called the Lagrangian, by the way. Here, let me just add this. The Lagrangian, like the DeLorean. All right, that's called the Lagrangian. Okay. All right, so let's see what this Lagrangian is. He has an x. I'm going to put this in front of me so you can see that I'm following the rules. So it has an x, a y, and a new lambda in it. So the way you create this is by subtracting these two functions. So it's f of xy, I'll write it one more time, minus lambda times g of xy. So it's xy minus lambda times, and remember the g function, the condition function, is basically all the terms, including whatever was on this side, right? So you minus it over to make it equal to 0. So this is your g function, whatever was equaling to 0 before. So basically all the terms, okay, to one side. All right, so this is my new function, yes? If you want, you can distribute. We usually won't. There it is. Okay, so it says if you want to find your answer, all you have to do is just find the critical point of this problem. Find the critical point of this Lagrangian. And that's going to be your answer. All right, well, fine. How do I find a critical point? Well, I'm going to take all three partial derivatives. This is now a function of three variables. Find all three partial derivatives, set them equal to 0, and see if you can solve that system. Okay, so the derivative with respect to x, well, there's an x here, and the derivative of that is y, minus 2 lambda, and that's it. That's all there is. The derivative with respect to y is x minus 2 lambda, and that's it. Set that equal to 0. And then the derivative with respect to lambda is negative 2x minus 2y plus 200. Set that equal to 0. I just want to point something out. This equation here, once you set this equal to 0, what is this equation really equaling to? The fact that 2x plus 2y is equal to 200, right? So really, that last equation there always turns into your condition, basically, right? So it's incorporated, basically. By doing this, we're incorporating your condition that 2x plus 2y should equal to 200 into this function, yes? So as you see, it's always part of the equation. It's always the last one. The derivative with respect to lambda, yes, is just your function g, right? The one that's set to equal to 0. Okay. All right, so the trick is, of course, there's a few ways of solving systems of 3 equations with 3 variables. It turns out for these specific problems, the best thing would be to pick the first 2 equations, solve both of them for lambda. So let me write this down. It's in the notes, it's in the textbook. Pick for the first 2 equations, solve for lambda, solve each for lambda, and set them equal to each other. Okay, so let's see what that means. Okay, so here it is. The first equation says y minus 2 lambda is equal to 0. That means y is equal to 2 lambda. It says solve for lambda. That means lambda is equal to y divided by 2. Yes. Okay. The second equation is x minus 2 lambda is equal to 0. That means x is equal to 2 lambda. Throw this over. Solve for lambda. That means lambda is equal to x divided by 2. Okay. And then lambda is y over 2. Lambda is x over 2. It said take these and set them equal to each other. So since both these expressions are equal to lambda, they must equal to each other. Or basically take this lambda, this y over 2, and plug it into this equation for lambda, right? Basically, eliminate the lambda out of both of them, right? So solve each of these for lambda and then set these equal to each other since they're both equal to lambda. Now this is pretty easy because if I multiply both sides by 2, what this reduces down to is that y must equal to x, yes? So out of the first 2 equations, I eliminated lambda and I created myself an equation in x and y. Now, what else do I have to use? I haven't used this third equation, yes, yet. So I know that negative 2x minus 2y plus 200 is equal to 0, yes? But what else do I know? I know that y must equal to x. So 200 is equal to 4x, x must be 50. Okay, plug it in back in, right? Y is the same thing as x, that means y must be 50 as well. So here's your answer, right? What we were trying to do? We were trying to find the maximum area of a rectangle with a perimeter of 200. So the width has to equal to the length, it turns out. Has to equal to 50 feet. Now that area will be 50 times 50, which is 2,500 square feet. Now, sure enough, if you look back to our chapter 2, we've solved several of those problems. And what happened is, as I had explained, if you want to maximize an rectangle, right? Find the rectangle of maximum area, what you have to do is you have to make it into a square. So if you remember we might have had, I don't know, 80 feet, 100 feet, whatever it was. We had a different number here, but either way, the solution to that problem was definitely that you had to have a square, right? So the width had to equal to the length. Okay. All right. So there's your first problem. Again, it would have been much, much easier to solve this problem by simply doing what? What we did in chapter 2. Solve this equation for x or y, solve it for y, plug it in here, make only one variable out of it, take the derivative, boom, done, the problem's done. Why did we solve it this way? Because again, it's nice to start a new problem or a new method with an easy problem, right? So this actually was not, in fact, that difficult. Setting these equal to 0, solving these systems, I nicely took my time solving it, but this was, in fact, super easy, yes? Why do we need this method? If the problems indeed turn out to be more complicated, yes, which they will in a bit. All right, so let's try one more maybe, and then see if we can start a different video after this. Okay. Here it is, one more. It says, find the maximum. So again, whatever you are finding, that critical point that you will find, be sure it's going to maximize this problem. Subject to this condition. So the first thing we're going to do is make a function out of this condition. And you make a constrained function out of it by throwing all the terms to one side of the equal to make it equal to 0, right? So that's your g function right here. Okay, all right. So out of these, we're going to create the Lagrangian. And that's simply f of xy minus lambda times g of xy. Okay. F of xy was what? X squared minus y squared plus 3 minus lambda times g of x is 2x lambda minus y lambda, and negative lambda times negative 3 is plus 3 lambda. Okay, so there it is. Now what did the problem say? How do we come up with a solution? We come up with a solution simply by finding your critical point. That's it. Your critical point is the answer. That's all we're asking you to do. Just find that critical point. So what's the derivative with respect to x? 2x minus 2 lambda. Okay. What's the derivative with respect to y? Negative 2y, right? There's a y, minus lambda. Okay. What's the derivative with respect to lambda? There's a lambda, negative 2x minus y plus 3, which is basically the opposite of your condition every time. Okay, set them all equal to 0 and solve. So what did we say the method is? Take the first two equations and try and get lambda by themselves. So the first equation says that if 2x minus 2 lambda is equal to 0, 2x must equal to 2 lambda, which means lambda is equal to x. The second equation, negative 2y minus lambda means negative 2y is equal to lambda. I already have lambda by itself. So what do I do out of these? Lambda is x, lambda is negative 2y. That means x must equal to negative 2y, right? So basically I replace the lambda with an x. All right, and then what do? We put this combination of the first two equations together with the third equation that was already in x and y and solve that system. So we got it down to a 2 by 2 system. Okay, here it is. X is equal to negative 2y, and negative 2x minus y plus 3 is 0. So it looks to me like the easiest way to solve this equation is by substitution. Right? Since it's already solved for x, plug it into here. So I get negative 2 times, instead of x, I write negative 2y minus y plus 3 is 0. So I get that 4y minus y plus 3 is 0. So 3y is equal to negative 3, which means y is negative 1. Okay, what do? Take it back and find the x, right? So x is negative 2 times y is negative 1, and that's a positive 2. So what is your answer? Your answer, the maximum occurs at the point of coordinates 2, negative 1, right? And what is that maximum? I should have made this. Plug it back in because you want to find that maximum value, right? Find the maximum of it. Well, the maximum value is occurring at 2, negative 1, right? And the maximum value is 2 squared minus negative 1 squared plus 3. So that's 4 minus 1 is 3 plus 3 is 6. That's the maximum value. Okay. All right, there it is. I'm going to stop this video. It's already half an hour, so that's enough. And we're going to continue with the other half of the section.